All right, these are problems 11 through 20, and I'm going to be beginning with question number 12. Using the same data, one student performs a test of a proportion is 0.85 and not equal to 0.85. A second, both use alpha. There's not an evidence. What's the following? Could have been the value of the test statistic. All right, so pretty challenging little problem right here. Let me reread that real quickly. All right, so the first one says not enough evidence. The second one says there is enough evidence. So let's draw a picture of this. And I'm going to start off with the second one because we know they reject. And their area in the tail is 0.05. And if I do second vars inverse norm of 0.05, this person will reject with any value less than negative 1.645. So any value less than negative 1.645, they're rejecting. And the reason it has to be less than is because they use that as their symbol. So that gets rid of this. It also gets rid of the negative 1.3 because it's not far enough to the left. So any of these two values, the second student would have rejected. So this is the second student. The first student did a two-tail test. And so basically they're saying, and they had a alpha of 0.05, and since alpha equals 0.05, that's their area of the tail is 0.025. Well, if I do a second vars inverse norm of 0.025, I'd have to have this value be negative 1.96. So anything left to negative 1.96, they're rejecting. So this one will reject with this. But we said, which of the following could have been the test statistic, because the second one rejected, but the first one did not. So it has to be between negative 1.645 and negative 1.96. So this answer, despite my circling, is letter B, because that's the one that's in between. Letter B is in between. All right, because this one rejected and negative 1.8 is in the rejection zone. But over here, 1.8 is above the rejection zone, so they failed to reject. All right, so looking at number 13, a company employs 10 executives. Each with a supporting secretary. The Human Resource Department wishes to determine the difference in mean salaries between the executives and their secretaries. Based on the most recent pay slips, a calculation is made for the mean standard deviation of the 10 executive salaries. And similarly for the 10 secretaries. A t-distribution is used to calculate a confidence interval for the distribution differences in the means. What is the principal mistake? Well, they have the values for the executives. They have the values for the secretaries, and so basically they're subtracting the two. Well, if you have the actual values, you've done a census. And if you've done a census, you don't need statistics at all because you have the actual values. All right, I'm going to need a pause. All right, question number 15. The prescription drugs Lipitor and Zetia are both known to lower blood cholesterol levels. In double-blind study, Lipitor outperformed Zetia. The 95% confidence interval estimated the difference in mean cholesterol level lowering was 21 to 37. Which of the following is a reasonable conclusion? All right. So first off, we never ever talk about probability. So any of those that had to do with probability are not correct. I always recommend that we go back to what are two things that we know we can say. One thing we know we can say is in when repeated sampling, we expect this to work 95% of the time. The other thing is we're 95% confident that we will capture the true population mean. In this case, we're 95% confident that this is, because this does not contain zero, we're 95% confident that Lipitor will outperform Zetia because zero is not in there. Because zero is not in there, we are 95% confident that that'll work. I need to pause this for just a moment. All right. A survey was conducted involving 50 of the 12,000 families in a town. In 2006, the average amount of medical expenses paid per family in the sample was 1,525 with a standard deviation of 430. Establish a 95% confidence interval for the total medical expenses paid by all families in the town. So they're not asking me to figure out the average. They're asking me to figure out the entire amount. Okay, so first off, the average paid per family was 1,525. Well, how many families are there? 12,000. So I should be able to just multiply those two values, 1,525 times 12,000, and I get 18,300,000. All right. So the next thing is I need to, my formula is X bar plus or minus T star S divided by square root of N. And if I use a T star, which is questionable, but if I involving 50 to 12,000, and they want to do a 95% confidence interval. So let's get our inverse T, second vars, inverse T, parenthesis 1 minus 0.95, close parenthesis, divided by 2, degrees of freedom 49. Now I'm going to get some value and it's 2. So this value is about 2 times my standard deviation was 430 divided by the square root of 50. So let's get that value. So 2 times 430 divided by the square root of 50. And I get 121.6. Well, that's my standard deviation per family, but there are 12,000 families, so I need to multiply by 12,000. And they did some ugly rounding, but my closest value is right here at 1,470,000. And that is a weird problem. And basically all they did is they said, instead of, we're not interested in the average per family, because the average per family would have been 1,005 would have been 1,525 plus or minus 2 times 430 divided by the square root of 50. That would be the average per family. But if I multiply by 12,000, I find the expected amount for the entire town. A little bit weird question. Number 18, in testing the null hypothesis mu equals 75 against the alternative mu is greater than 75, a sample from a normal population has a mean of 76.9 with a corresponding t-score of 2.0 0.23 and a p-value of 0.075. Which is the following is not a reasonable conclusion? Well, first off, a p-value of 0.0175 tells me there's a 1.75% chance that I would get a test statistic as extreme as 76.9 if this is really true. So that's fairly rare. All right. Which of the following is not a reasonable? If the null hypothesis is assumed to be true, the probability of obtaining a sample mean as extreme or more extreme is only 0.1075. That's the definition of a p-value. That's true. In all samples using the sample size and the sampling technique, the null hypothesis will be wrong 1.75% of the time. That's not what that says. It says there's a 1.75% chance we would get something like this if the null is true. This is false. All right, so letter B is our answer for number 18.